Hi, I'm Brian, and today I'm presenting GRiD, GPU-accelerated rigid body dynamics with analytical gradients. GRiD makes it easy to use the GPU with any algorithm that requires rigid body dynamics, and is performant, providing a 7.2x speedup over a state-of-the-art CPU implementation, and maintaining a 2.5x speedup when accounting for I/O overhead. But you might be asking, why GPU rigid body dynamics? And there's two reasons for that. First, rigid body dynamics and their gradients are bottleneck operations for many state-of-the-art planning and control algorithms. For example, they consume 30 to 90% of the total computation time of nonlinear MPC. Second, frequency scaling ended in around 2005, and CPUs just aren't getting much faster. So we need to look beyond the CPU and exploit large-scale parallelism on alternate hardware platforms like the GPU to continue to get through these sorts of computational bottlenecks. So let's talk a little bit about GRiD's modular design. GRiD is designed to take a user's input URDF and output optimized CUDA C++ code. Along the way, we also include modules that help you validate your outputs and perform performance benchmark analysis against optimized CPU implementations. GRiD currently implements inverse and forward dynamics, as well as their gradients with respect to state and position, and the direct inverse of the mass matrix. And all of this can be done for any URDF with fixed, prismatic, and revolute joints. We're currently actively working to expand this effort. You can find the most up-to-date version of our code at github.com/robot-acceleration, and we welcome any community involvement to improve and extend our package. Now let's talk a little bit about what makes GRiD so performant, and that's its optimizations. So what GRiD does is it exploits the structure of each robot model to minimize memory usage and optimize latency. So for example, if we take the very serial gradient of the RNA algorithm, we can extend or refactor the algorithm to expose parallel loops of unified operations which can be efficiently computed on the GPU. And then, within the remaining serial loops, we can actually note that all of the operations within each level of the kinematic tree can also still be computed in parallel. We also leverage this branch structure of the kinematic tree to note where there are sparsity patterns in the memory needs of these various variables and compress and remove them to optimize memory usage. So now let's look at some benchmark analysis results of GRiD as compared to a state-of-the-art CPU algorithm. Here we've plotted the mean computation time for running the gradient of forward dynamics on the CPU and the GPU for different n numbers of computations at a time. We see that GRiD scales to higher numbers of computations, leading to 1.3 to 5.3x speedups in pure computation. We also find that as we increase the complexity of the robot model, moving from the 7 degree of freedom EWA model to the 12 degree of freedom HiQ model, all of these increase, leading to overall up to a 7.2x speedup. However, there are limits to this computational scaling, and we see by using the 30 degree of freedom Atlas robot that after about 64 knot points, while we have now increased to a 4.9x speedup, which is faster than the speedup on HiQ, we cannot speed up any more than that, and the scalability breaks down, leading to still only a 5.0x speedup for 256 knot points. And this is because the Atlas computation requires a lot more memory usage, and we saturate the GPU at around 64 knot points. One other thing I want to note is that I/O can be problematic and really cuts into our speedups, cutting the up to 7.2x speedups down to up to 2.5x speedups across all the robot model. This is why we hope to actually integrate GRiD into trajectory optimization algorithms running fully on the GPU, although we do note that you still get speedups basically across the board by using GRiD, and which really shows the power of parallelism. So in conclusion, GRiD is a URDF to optimize CUDA C++ library designed to provide GPU acceleration for rigid body dynamics and their analytical gradients, showing up to 7.2x speedups and maintaining a 2.5x speedup when including I/O over state-of-the-art CPU algorithms, making it easy to use the GPU. We encourage you to check out all of our libraries and packages at our GitHub organization, github.com/robot-acceleration, and welcome any community involvement in improving our packages. Thank you.